So I'm going to try and actually speed run the intro of this video here, because I have actually 3 things I need to say, and I do want to get this video done quickly so I can upload it better. So I've practically given up on recording regularly. Whatever promises I've made before are just unrealistic for my current standards, because I recently started a new grade. So I do apologize for that. I also apologize for any video quality decreases, because I'm kind of out of practice in doing this, and yeah, I'm just not that great anymore. And lastly, I have finally recognized the fact that using a microphone makes my voice sound a little too high, at least on my devices. So I'm going to stop using them, and I'm just going to see how that works. If the volume's too low, then I'll just use them again. So this is a constant in a family of constants called the Champernowne constants. They are defined as 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, written like this. Now, this constant looks incredibly easy to understand, and to explain the creation of this is also very easy. However, it is irrational and most likely transcendental as well, which is actually kind of interesting. You can sort of see that it's irrational because, well, they don't repeat, do they? They just keep on going. But transcendental, to be honest, I'm not so sure, but I do believe you can't write them using radicals or anything like that. So the main goal for today is just going to be finding a series representation of this Champernowne constant. Now, this is the Champernowne constant for base 10, because we use base 10 in our mathematic measurements. But there's also some other Champernownes. For example, Champernowne 2 is equal to 0. Okay, now we start. 1 is still 1. 2 is 10. 3 is 11. I'm saying 11, but it's actually just 1, 1. 4 is going to be 1, 0, 0. 5 is going to be 101. 6 is going to be 1. Oh, didn't mean to write 6 there. It's going to be 1, 1, 0, and then so on, and base 2. The real solution should be this thing transferred back to base 10, but I feel like this makes better sense. So the goal of this video is not only to figure out one series representation, it is a series representation for all of the Champernowne constants. And it creates a kind of interesting but really cool sum, including a series including a sum inside it. And overall, I feel like it's going to be very interesting. So first of all, we're going to realize this constant's more complexity when you're looking at like irrationality or something, and that's mostly because there are different digits. Once you get to a 9 here, you get 10, and each digit is going to be 2. Each additional number is going to be 2 digits smaller than the last. So how about we categorize this? We just write 0.1, 2, 3, 4, 5, 6, 7, 8, 9. And then we'll say plus 0. Some amount of zeros, okay, 9 zeros, but writing it like this is going to make it easier when we go further on. And then 10, 11, 12, and then all the way up to 99. Cool. And then you're going to then add 0.0, something, something, 0, and then it's going to be 100, 101, and then all the way up to 999. And then it just adds on forever like this. Now, writing in this form lets us use summation notation, and here is where things are going to get a lot more interesting. So, for this first one, this is going to be kind of easy. This is going to be the sum. N starts from 1 to 9. There's a coefficient of n, and then it's 10 to the negative n. Because it starts at 1, n starts at 1, and this thing starts at 0.1, which is 10 to the negative 1, and then it goes smaller by 1 digit every single number you go. So that's the first sum, okay, it's not that complicated. And then we're going to add the second one. So sum. N is starting from 9 is already taken, so we have 10 to 99. And then now we're going to do n again, and then it's going to be 10 to the minus. How many digits are in... The amount of digits in here is the number of zeros in here. So in this case, it's going to be 0. It's going to be 9. And then minus... now, if we look at the 10-digit ones, each number is going to take up 2 digits. So we're going to have the 2 here times n. Now, here's the thing. If we're going to plug in n equals 10 to this one, this is 10 to the negative 9 minus 20, which is going to be a much smaller number than this thing right here. So what we want is this term to start at 1 when n starts at 10. And how we do that is we just minus 9. I hope this makes sense, because this is the number of zeros, and then when n is equal to 10, n minus 9 is equal to 2, is equal to 1, but we're multiplied by 2, so it's 2, and then that's going to be 9, that's going to be 2. So, in theory, this should make sense. And now we then move on to the third sum. N is equal to 100, because 99 is taken, all the way up to 999. And it's going to be the same general thing. We have an n here, we have a 10. Negative 9 minus. How many 2-digit numbers are there? Well, if you think about this, 10 is the first, 11 is the second, 12 is the third. So basically, you're subtracting 9 from it, and then you get the number it is. So in total, we have 99 minus 9, which is then going to be 90 2-digit numbers. Now, each of these 2-digit numbers have 2 digits in them. So we have 2 times 90. Okay, interesting. And then the same thing here. So minus, and then this is going to be 3 digits. So we have 3. And then n minus, and then this should start at 1 for n is equal to 100. So minus 99. Okay, and then you add, and then so on. So this should make sense in my head. This makes sense in my head. I don't know about yours, but I hope this does as well. Now we can just figure out a pattern, a general pattern, and we have an infinite summation taking care of that. So I'm going to start a new summation symbol, this time k. It's starting from, interesting. So, interesting, yes. We're starting from n is equal to 1 to 9, and that's going to be the 1-digit numbers. So k basically represents the number of digits in our number. So it's going to start at 1, and it's going to go to infinity. Right, because there's numbers that are infinitely long in this number here. Now, k equals 1 to infinity. There's going to be another sum, and it's starting from. For k is equal to 1, n is equal to 1, and then 10, and then 100. So it's 10 to the k something. But if you plug in 1 to here, that's going to be 10, not 1. So instead, we're going to have to do 10 to the k minus 1. And that's going to be the starting value. Now, for this 99, if we add 1 to each of these, we get 10, 100, and 1,000, which are just going to be 10 to the k. So it's going to be now 10 to the k minus 1 for our top value. And this is already kind of wild, you could say. Just a sum here. And then we have an n, and then we have a 10. Now, I'm going to write this term first. So for the k-digit numbers, for the k-digit numbers, it's going to be minus k times n minus. Now, when n is equal to this thing, we want this expression to be equal to 1. And how we're going to do that is we're just going to subtract 10 to the k minus 1, and then we're going to then add on 1, like that. Now we have something slightly a little bit different. And here we're going to write 9 as 1 times 9. So we have 1 times 9 minus 2 times 90. And then the next one is probably going to be 3 times 900 based on the pattern. So here we actually have another, a smaller sum. This I'm going to use I. It's going to start at. So, we're starting at 9 here, which can be written as, 1 times 9. So here, 1, I think, should be our I, certainly, because we have 1, 2, 3, and so on. So I starts at 1. Now, I ends at, so if you look at this one, here k is equal to 3, I believe. Yes, 3. Because 10 to the 2 is going to be 100, and that's 100. So here, it ends at 2. It ends at 2, which is conveniently k minus 1. So the top value for this one is going to be k minus 1 for the sum. Now it's going to be easy. We're just going to find I. And then we have 9, 90, 900, and so on. So we can take apart that 9. And then we get a 10 to the for I equals to 1, it's 1 times 9, which is 1 times 9 times 10 to the 0. And this is just going to be I minus 1 then, if we're going to follow the pattern. And so here we go. This is our complete series representation. Now, obviously, you could make it more nice to look at if you drag this sum with a 10 on top of it down, because that has nothing to do with n whatsoever in this situation, right? So here we have a sum. A series, actually. K starting from 1 to infinity. And then, from now on, x10 or xn, in this case, is just going to be 10 to the something. So it makes it look a little bit better, at least for our notation. I equals 1 to k minus 1, and then we have, 9 here. Oh, wait. I have to do a minus sign as well. Negative 9, sum, and then I times 10 to the I minus 1. And then we have another sum. N is equal to 10 to the k minus 1. 10 to the k minus 1. And then here we have n times 10 to the negative k times n minus 10 to the k minus 1 plus 1. Okay. This is our series representation of the Champernowne constant for base 10. But there are different Champernowne constants. There are a countable infinity of these. Basically, one for each base here. So now we want to generalize this, right? And you can already sort of see the generalization because 10 is kind of a big number. So anything that is related to it, like this 9 here, you can just say that it is n minus 1. And so in this case, yeah, you can say this is k equals 1 to infinity of x times x base minus, and then this is going to be base minus 1, and then this sum 10 is going to be replaced by the base. 10 is going to be the base, 10 is going to be the base, 10 is going to be the base, 10 is going to be the base. But obviously, when I do math, I like to do it more. How do I explain? I don't just want to be looking at examples and making assumptions. So I do want to record this last little bit where we change up the definitions here. We change this entire thing. Because, well, what's better than solving one question? We solve a countable infinity of them. Oh my god, this room is actually kind of hot. Cn, base n. Now, I'm going to actually write a different notation, because we're going to write 1 as 1n, but obviously this represents a number. Oh wait, never mind, we need a 0 point. We need a 0 dot. So obviously, this is going to be 1n, but this represents a number, not a decimal, so I'm going to just do a bar on the top. So that just means that it's a decimal representation, pretty much. And then we have a 2n, 2n, and then 3, and 4, and all the way down. And then this is base n, pretty much. We now start to look at dividing it up by base like we did before. So this is now equal to 0. I'm not going to do that anymore, because that's going to be way too complicated. So I'm going to go directly to the sum. Now, if we're going to start, actually, we need a new index, j. J is going to be starting at 1, right? And then, if we're going to find the biggest first digit number for base n, it's going to be n minus 1. Because if it's going to be n, it's going to be written as 1, 0. So 1 to n minus 1. And then, is this 1 to n minus 1? I think it is 1 to n minus 1. I'll hope it is 1 to n minus 1. Anyway, so, now we have, first of all, j, right? And then n to some power. So, if these are all 1 base numbers in this category, in this base right here, so all of them are just going to be 1 digit. Oh, wait. All of them are going to be 1 digit further than the previous one. That's what I'm going to say. So, this one, I hope this one makes sense. I just That's the best explanation I could. I saw this in my head, okay, I didn't write it down or something. And then you're gonna add, right? So what's the next number? And the next number is gonna be n, of course, and that's gonna be written as a 2-digit 10. So what is the biggest number that you can express with 2 digits of base n? This one, I think it's gonna be, so n squared is gonna be 100, so that's gonna be n squared minus 1, pretty much. And now, we can do, it's pretty much the same thing. So j, and then n to the. Now, here's the biggest problem. How many, it's not even the biggest problem, it's just a small problem. How many digits are there when it comes to this? This is going to be starting from 1 to n minus 1, and then each one is going to be, it takes up 1 digit. So it's going to be all the numbers between 1 and n minus 1, which is going to be n minus 1. Okay, and then minus on, of course. And then minus. Now, if we're going to do 2 digits at a time, this is going to be now 2, right? And then it's going to be j minus, and then when j is equal to n, we want this thing to be equal to 1. So it's just equal to j minus n plus 1, pretty much. And that's the start of the pattern. And now we can just continue, right? So we can then add the sum. J is equal to n squared minus 1 is going to be taken, so n squared to n cubed minus 1. This is going to be all of those that take up 3 digits, 100. And it's just pretty much the same thing as before. We're still going to write j, and then n to the minus. N minus 1 is from before. Now, how many digits are in here? It's kind of interesting. So, each one of these numbers over here, they take up 2 slots, 2 places, 2 digits, pretty much. So minus, it's going to be 2 times something, right? And then this is going to be the number of numbers from n to n squared minus 1. So if we're going to find this example, there's going to be n minus 1 things, which is going to be n minus 1. Let me actually think for a second. N minus 1 minus 1 plus 1. So the same thing, n squared minus 1 minus n plus 1, n squared minus n. So I have n squared minus n, or you can factor out an n here, and you get n minus 1 times n, and then minus. Each of these are going to be 3 digits, so we have 3, and then. So we have j here, and then when j is equal to n squared, we want this thing to be equal to 1. So we're going to do minus n squared, and then plus 1. Okay, so I think that's before. And then dot dot dot. Same process, now we're going to use summation, pretty much. A series notation. So we have a new index. What would our new index be? I think we're still going to use k, because that's not used before. Again, it's going to start at 1 to infinity. K is the number of digits here for base n. And then now, obviously we're going to have another sum. J is starting from 1 and n squared. That's obviously going to be n to some power. And then when k is equal to 1, this starts at 1, which is going to be n to the 0. So pretty much this is n to the k minus 1. Because it follows a linear pattern, or at least the exponent does. And then now it's just, how would I explain this? Now it's just, this power is 1 more than this power. So we have n to the k up top. And obviously it's going to be minus 1. Okay, cool. And now it's going to be j, n to the minus. Like before, I'm going to write this thing first. So there's k digits, so this would be k. And then, if this is k, this is going to be k minus 1. So we have j minus n to the k minus 1 plus 1. Okay, interesting. I hope that you can verify this. And then minus. Okay, interesting. So we have n minus 1, 2, n minus 1, n. If we were just going to continue doing this, because if we're going to do this, it's going to be n cubed minus 1 minus n squared plus 1, which is going to be n cubed minus n squared, which is going to be n squared times n minus 1. So it's a sum. This thing remains the same. So this is a constant factor. And then we have a sum, I did we use I? I don't think we used I. I is starting from, and then once again this coefficient is 1, so I'm going to start at 1, and then in this case k is going to be 3, and this ends at 2, so it's going to be k minus 1 then. Okay, and then 1 n squared n something and so on. But we're starting when I is equal to 1. N's exponent is going to be 0. So we have n to the I minus 1. And of course there's an I over there. Okay, that's all cool. Now we can do the same thing before where we use the exponent notation. And we'll finish off our series representation. So from 1 to infinity, of course. And then I'm going to use xn. Remember, that's going to be n to the something. Minus n minus 1. And then the sum. I is going to be equal to 1 to k minus 1. And then I times n to the I minus 1. Okay, cool. And then this other sum. Sum. J is going to be starting at... J is going to be starting at n to the k minus 1. All the way up to n to the k minus 1. Okay. Final step. J, n to the minus k. J minus n to the k. K minus 1, of course. Plus 1. That's going to be the entire series notation for the... Oh. Erasure fell. Erasure? Interesting. That is going to be the entire... Not the entire. That is going to be a generalized series representation for the Champernowne's constant of base n. And, like I said, why solve one series representation when you could just solve an countably infinite algorithm? And indeed, you can plug pretty much any number n into this as long as it's integer, but I'm not sure if real numbers actually work in this. They might, but I don't think so. So, I'm going to end it off there. This is going to be the sum. It's kind of crazy, kind of cool, kind of interesting. I hope you enjoyed this journey, and I will see you whenever I upload next, although it's probably not going to be any periodic timing. So, I'll see you until the next time I record. Bye.